In this lesson, we're beginning our study of chemical reactions, the processes that rearrange atoms to form new substances. Up to this point, we've focused on bonding, structure, and polarity. Now we're going to see what happens when substances actually interact and change. By the end of this lesson, you'll be able to balance chemical reaction equations using either the tally method or by balancing by inspection. So in chemical reactions, the general reaction equation is that the reactants are going to react, rearrange, combine in some fashion to produce the products. Now, this may seem like a very obvious thing at this point in time, but a little bit later in the semester, I found that students start getting a little bit confused about which side the reactants are on and which side the products are on. If it helps any, just think role play as far as keeping the which side each is on. So, for example, if you take some bricks and lumber and cement all by themselves, they aren't really useful. It's just a big pile of building materials. But if you rearrange them in some useful fashion, it will produce a product, such as a building. So we've seen this example before. The law of conservation of mass. Matter is neither created nor destroyed during a physical or chemical change. We're just talking about chemical changes right now. And remember, I summarized this by saying what goes in must come out. So the example we saw before was that 23 grams of sodium reacts with 35 grams of chlorine gas to form sodium chloride, and how much sodium chloride was formed. And so using the general reaction equation, we said that, well, if you have 58 grams of stuff going in, you better get 58 grams of stuff coming back out. So now let's add to this a little bit. If you notice, I have used the symbols for sodium and for sodium chloride. But chlorine currently is still just written out in words as it was before. And that is because chlorine is diatomic. And so the first thing I want you to do is kind of think about the other of the diatomic elements. I always call them the Magnificent Seven. Remember, hydrogen is one of them. Hydrogen is special in a lot of different ways. And then the rest of the seven start at element number 7, nitrogen, and they make a 7. So it'll be hydrogen, then nitrogen, oxygen, fluorine, chlorine, and bromine, and iodine. All right, so now let's put Cl2 in there instead of the word chlorine. Let's draw some pictures, because pictures are worth 1,000 words. So we have sodium atom. They are not diatomic. We have a chlorine molecule, and it says we're making sodium chloride units. Now, it's if the way we have it written right now, we can only make 1 unit of sodium chloride, and we have a chlorine atom left over. The problem didn't say anything about having chlorine atoms left over, so this is why you need a second sodium atom to make sure all of the chlorine has something to react with. So when you are writing out balanced chemical reaction equations, what you're doing is you are invoking the law of conservation of mass. You're making sure that if you started out with 2 sodium atoms and 2 chlorine atoms, you better end up with 2 sodium atoms and 2 chlorine atoms. So the tally method of balancing is where people typically start. So all we're going to do is we're just going to make a tally on the reactant and the product side of how many of each type of atom we have. And then we're just going to compare them to make sure that they are the same on both sides. I always kind of call this bean counting. So with this first part, we have 2 hydrogens, 2 hydrogens. Hydrogen's fine. Next part, we have 2 oxygens and 1 oxygen. So we have to fix this 1 oxygen on the product side so that it will be the same as it was on the reactant side. So we're going to multiply, and you always have to multiply. We're not adding, not subtracting, not doing any other funny math with this. So we say, all right, 2 times 1 oxygen will give us 2 oxygens. If you multiply down here in the tally, you need to multiply up here in the actual reaction equation. So we're going to multiply H2O by 2. So now we have 2 oxygens. But the problem is we have now changed our number of hydrogens because you multiply the whole compound by 2. So we have 2 times H2. So we have a total of 4 hydrogens on the product side now. So that means we get to come back over here to the reactant side, multiply that one by 2. And so we're going to put a 2 up here in the front of H2. So these numbers in the blanks are called coefficients. The little numbers are subscripts. So the little numbers tell you how many you have of each atom in the compound, whereas the coefficients tell you how many of each atom or molecule is participating in that particular reaction. They are reaction specific. And they act like multipliers when balancing reaction equations. Some other rules, you always have to have whole numbers. You can't use fractions. And you have to have the lowest whole number that are possible. So in this case, 2, 1, 2 would be fine. And I typically don't write the ones in the blanks, but if you want to, that's fine. But 4, 2, 4 would be wrong. Oh, and you can never use zeros. I get a 0 every now and then because people are like, well, I can't get this to balance, so I'm just going to get rid of it altogether. That would be violating the law of conservation of mass. You can't do that. So here's another one. This is an example of a wordy reaction. So you see we have zinc metal. So zinc, its standard state on the periodic table, is a metal. It's a solid. So that just means it's just zinc all by itself. These little letters in parentheses indicate the state of matter, which is part of the reason why I wanted to include this. So if it says zinc metal, you'd say that's a solid. So zinc in a solid state plus lead 2 nitrate. Lead is a metal, so you do your swap and drop. You write the correct formula. Ends up being Pb NO3 twice, and it says it's an aqueous solution. So even though it's not a state of matter exactly, there are so many chemical reactions that get done while the things are dissolved in water that it gets to be notated like that. So AQ means aqueous. It's been dissolved in water. And then reactive form means that's the arrow. And now we have zinc 2 nitrate, or just zinc nitrate. You don't really need the 2. And lead metal. So we would have these as the products. So now we're going to use our tally and set up the tally on the other side. Now, one of the tricks is that if you see that you have a polyatomic ion, and we know we do because it's in parentheses, you look at the other side and see if you still have that polyatomic ion. You can simplify the balancing if you just keep the polyatomic ion together. So here we have 2 nitrates on the reactant side, which is why I wrote that there, and then 2 nitrates on the product side. You should also make it easier on yourself by writing them in the same order so you can go back and forth and compare easily. So if it's a really, really long equation, you won't get confused. So that's why I have it as zinc, lead, and nitrate over on the product side, even though it's not written in that order on the product side. All right, so we've got our tallies. We're ready to do our checks. So 1 zinc, 1 zinc. That one's fine. 1 lead, 1 lead. That one's fine. 2 nitrates, 2 nitrates. Those are fine. So that means that this reaction equation is already balanced. And as I said before, you want to have the lowest whole number coefficients. So 1, 1, 1, 1 is correct. 2, 2, 2, 2 will be wrong. All right, another word of reaction. So let's just go ahead and write it out. So state of matter gas would be a little g. And if the state of matter is a liquid, it's a little L. So we do our tally. And we start out. All right, so we got 1 aluminum, 1 aluminum. They're fine. 3 bromines, 2 bromines. So we want to find the lowest whole number multiple of 3 and 2, which is 6. A lot of times what I tell people is you can kind of you have to check to make sure you're not getting higher order coefficients, but you can say, all right, well, I'm going to multiply the 3 by 2 and the 2 by 3 to get them balanced. So I multiply the 3 bromine by 2, so I have 6 bromine on one side. So I multiplied my bromine containing part by 2, so that means I need to put a 2 up here in front of the aluminum bromide. Likewise, I multiplied the bromine on the product side by 3, so I put a 3 in front of the bromine liquid. So now I have 6 bromines on both sides. All right, so we multiplied our aluminum bromide by 2, which means I changed the number of aluminum. So now the aluminum is no longer balanced. We have to fix the balancing of the aluminum. I always kind of picture this process as sort of like a seesaw. Change one thing and you look at how it affects the other side. You kind of keep seesawing back and forth until you get it all balanced out. So now we have 2 aluminum, so we got to fix our aluminum on the product side by multiplying by 2. Whoops. So we multiply our aluminum chloride by 2, which means we have to multiply our chloride on the product side by 2. And then we got to multiply the chloride by 3 over on the reactant side. So now we have coefficients of 2, 3, 2, 3. All the blanks are filled up. That's the lowest possible whole numbers you can have, so we can stop there. All right, so once you've done this for a while, you can start, you don't have to keep writing down the tally method, and you're going to start doing an alternative balancing technique, which is called balancing by inspection. I've heard some people call it guess and check, but I don't really like that because there is a system to it. So first let's write down the skeleton reaction equation. So we have phosphoric acid and sodium hydroxide is going to form water and sodium phosphate. All right, so the strategies here, let me get my pen, are that you want to look for your largest subscript. And so a lot of people kind of zero in on the phosphate. Now, like I said, if you have a polyatomic ion on one side, you want to check the other side. And so what I'm going to do is I'm going to draw a circle, or try to anyway, around the phosphate. Look at the other side. It also has 1 phosphate. So phosphate is actually not the largest subscript. So then I kind of see the next big subscript I see is hydrogen. But the problem is the hydrogen is in 2 different places. Let me see, write that down. So if in multiple places on the same side of the arrow, save for the end. So we're going to do hydrogen last. So that means the next one that we have is sodium. So that's why it says first pass, balance the sodiums. So on the product side, we have 3 sodiums. On the reactant side, we only have 1. And if it helps, add little subscripts of 1s, even though you're not supposed to show those in the formulas. So we want to multiply our sodium hydroxide by 3. Come down here. So now we have 3 sodiums on both sides. So now we have changed the number of oxygens that aren't in phosphate so that we have, let me put it back on laser pointer for a moment. So now we have changed the number of oxygens on the reactant side. So now we have 3 oxygens instead of 1 oxygen. So now we need to look at the other side. We see that we only had 1 oxygen to begin with. So we're going to multiply our H2O by 3 so that we will have 3 oxygens on both sides. So now the oxygens are balanced. And then we need to check our hydrogens. That's the only one that's left because we've already determined that we have the phosphates are balanced. So I'm going to do the product side first. So we have 3 times 2, so we have 6 hydrogens on the product. Now the part where people, when they first start doing this, tend to make a lot of mistakes is they ignore that little plus. And that plus is why we had to save the hydrogen for the end. So here we have 3 hydrogens. So pluses are still plus. And then we have 3 more hydrogens. So we have 6 hydrogens on both sides. So the reaction equation would be 1, 3, 3, 1. Let's look at another example. So this one, I cut out all of the animated text so I can just kind of go through it by hand. So you look for your biggest subscript that doesn't occur in multiple places. So we see that we have oxygen in multiple places over here on the product side, so oxygen last. All right, so hydrogen is biggest subscript anyway, so we're going to start with that. So we have 4 on the reactant side, so we need a 2 in front of the H2O. That gives us 4 hydrogens. We're not doing anything with the oxygen yet. We have 2 carbons on the reactant side. Currently we only have 1, so we got to put a 2 in the blank. Now the only element that's left is oxygen. We have 2 times 2, which is 4 oxygens. I'm going to write it out because otherwise it looks like a 0. Plus 2 times 1 from the other part gives us 6 oxygens on the product side, which means we need a 3 in front of the O2. So the coefficients would be 1, 3, 2, 2. There we go. All right, so the last one, I kept the text in there. So the first thing you want to do is identify the biggest subscript. So the biggest subscript in this case is, we got 5 oxygens, and we have 2 on the other side. So that means we're going to multiply our oxygen by, on the reactant side, by 5, and by 2 on the product side. So now we have 10 oxygens in both sides. We have multiplied our diphosphorus part by 2, so now we have 4 phosphoruses, or phosphori, I don't know which is right. So that means we're going to have a 4 in front of the phosphorus. And so that one's done. All right, so wrap up. So remember, the general reaction equation is the reactants are going to rearrange to produce the products. The reason why we have to balance chemical reaction equations is due to the law of conservation of mass. You don't want to be destroying your atoms or creating atoms out of nothing. You have to have the same number of each type of atom on both sides. Remember, the coefficients are multipliers. You're not adding, you are multiplying by that number. And the rules are they always have to have the lowest whole numbers. They are never 0. And they are never 0. End right there. So we saw that there are 2 general balancing approaches. So the tally method, that's where you write each type of atom underneath, and you just keep going back and forth with the coefficients until they're all balanced out. One of the tricks you can do with this, well, for both of them actually, is if you see that you have polyatomic ions, draw a circle around the polyatomic ions, or kind of group them in some fashion so that you simplify the task a little bit. And then the other technique is balancing by inspection. And the general, it just takes practice, but the general strategy is to look for your biggest subscript of something that's by itself. You got to save the ones that show up in multiple places on the same side of the arrow for the very end. And you keep going back and forth kind of in a seesaw fashion until the reaction equation is balanced. All right, so that's it for our introduction to reactions. Next time we're going to be looking at different types of reactions and a little bit more balancing. And so that's it for this lesson. Thanks for listening.